Very good morning, students. Today we are going to discuss about chapter 8, unit 4, transient response of control system. So up till now we have discussed block diagram, various symbols, how to draw the overall block diagram, how to reduce the block diagram, and how to solve the block diagram for servo and regulator problem. Today we are going to discuss about the response equation for a unit step change to the load variable or to the set point. So in this chapter we are going to consider the unity feedback control system. So that unity feedback control system is shown in the figure, which consists measuring element h is equal to 1. So there is no block diagram, no transfer function in the feedback path, and instead of final control element and controller, only we will consider only a controller having a transfer function is GC. So this will be your unity feedback system, where you have a control variable, measuring variable, set point, error. Then there are two blocks. One is consisting a controller having a transfer function GC, then M manipulated variable, load variable, and unity process, unity feedback process, that is first order system. Is it right? So its transfer function is 1 upon tau s plus 1. So this is called as a unity feedback system. This unity feedback system is used to write the overall transfer function. Now this overall transfer function can be written as the ratio of control variable to the set point C by R, which is known as servo mechanism problem, and the relationship between a control variable and load variable, that is C by U. So this is known as a regulator problem. So these two are obtained for this unity feedback control system. So it's very essential to define offset now for this case, where offset is defined as it is a difference in magnitude of set point and the control variable, and this is a difference at steady state condition of the system. So what is offset? Offset is the difference between a set point and control variable. So it is R infinity minus C infinity. R infinity means it is a set point value at steady state, and a C infinity is value of control variable at steady state. So these are nothing but the two values, and its difference will give you the offset. This value of offset is different for the different controllers and its mechanism. So as you know, offset is different for different controllers. So objective of this chapter is to find out what will be the offset for proportional controller and proportional integral controller. Only these two controllers are in your syllabus, except PD and PID controllers. Okay, the derivations has been solved in the notebook, but it is not in a syllabus. First of all, we will discuss about the proportional controller for servo mechanism control problem. So again you have to go to the unity feedback system. So here we are going to derive four derivations: proportional controller for servo mechanism control problem, proportional controller for a regulator mechanism control problem, proportional integral controller for servo mechanism, proportional integral for a regulator mechanism. So these four derivations we are going to solve in this chapter, where for all these derivations we are going to consider this unity feedback control system. So we'll start the derivation. So you have to write first of all what will be the C of S by R of S. So what will be the C of S? C of S by R of S will be equal to nothing but C is control variable, R is a set point. So C by R is equal to, numerator will be GC into 1 upon tau S plus 1, And what will be the denominator? Denominator will be 1 plus gh. So 1 plus gc into 1 upon tau s plus 1. So this will be your denominator. So you have to solve this equation and you have to bring it in form of c by r is equal to gc upon gc plus tau s plus 1. Now for in case of proportional controller, gc is equal to kc. So you write c by r is equal to kc upon kc plus tau s plus 1. Now you have to divide by the constant of the denominator, constant terms of the denominator. So we'll divide it by 1 plus kc to the numerator and denominator. So kc upon 1 plus kc upon tau upon 1 plus kc into s plus 1. Is it right? So now you can write this equation as kc upon 1 plus kc 1 upon tau dash s plus 1, where we write tau dash is equal to tau upon 1 plus kc. So once you write this, then you can introduce the step change and you can find out its inverse Laplace. So now here we'll introduce a unit step change is given to the set point. So R of s is equal to 1 by s. What the equation becomes? C of s become kc upon 1 plus kc into 1 by s into 1 upon tau dash s plus 1. So now you have to solve this equation by partial fraction. Okay, otherwise you can directly write this unit step change for first order system like the next derivative, next term, next equation, kc upon 1 plus kc is equal to bracket 1 upon s minus tau dash upon tau dash s plus 1, bracket complete. If you will solve this bracket, you will get above term 1 upon s 1 upon tau dash s plus 1. So now for this term you can find out its inverse Laplace. C of s becomes c of t, kc upon 1 plus kc remains constant, 1 becomes 1 upon s becomes 1 minus e raised to t by tau dash. So this is called as a response equation for the proportional controller mechanism problem. Now what you have to find out? You have to find out the steady state value for control variable at t is equal to infinity. So if we put c of t, if we put t is infinity there, equation you will get kc upon 1 plus kc. What will be the r infinity? So you know that unit step change is introduced into the set point. So r infinity is 1. So you can write the offset from this. Offset will be r infinity minus c infinity is equal to 1 minus kc upon 1 plus kc. So the offset is equal to 1 upon 1 plus kc. So this will be the offset for proportional controller for servo mechanism control problem. It's very easy. If you solve this derivation once or twice, you will understand everything. Next is about the proportional controller for regulator mechanism control problem. So in case of regulator control mechanism problem, the overall transfer will be written as c by u. Is it right? So the equation will be written at constant value of c set point, because in regulator mechanism problem set point remain constant. What is the c by s? C by u. C of s by u of s is equal to, again you go to unity feedback system, is equal to 1 upon tau s plus 1 upon 1 plus gc upon tau s plus 1. So you can solve above equation and you will get 1 upon gc plus tau s plus 1, where you can write for proportional controller gc is equal to kc. So c by u becomes 1 upon 1 plus kc plus tau s. So now you have to solve this equation by introducing the step change. So c by u, again you have to divide by 1 plus kc, the constant term. So it becomes 1 upon 1 plus kc, 1 plus tau by 1 plus kc into s, where tau dash is tau upon 1 plus kc. So if you solve this, c of s by u of s become is equal to 1 upon 1 plus kc into 1 upon tau dash s plus 1. Is it right? So Now, if we introduce a unit step change into the load variable, u of t is equal to 1. So, u of s is equal to 1 by s. So, you can introduce this unit step change into this. It becomes u of s is equal to 1 upon 1 plus kc 1 by s into 1 upon tau dash s plus 1. Again, you can solve this bracket by only subtracting the terms. So again, c of s is become equal to 1 upon 1 plus kc bracket 1 upon s minus tau dash upon tau dash s plus 1 bracket complete. Again, you can take its inverse Laplace. What will be inverse Laplace? C of t is equal to 1 upon 1 plus kc into bracket 1 minus e raised to t by tau dash. So this equation 8.13 is the response equation for proportional controller for a regulator mechanism control problem. At steady state t infinity, the equation can be written as C of infinity is equal to 1 upon 1 plus kc. What is value of r infinity? Set point is 0, so r infinity is 0. We can find out the offset. Offset is equal to r infinity minus c infinity. You get offset is equal to minus 1 upon 1 plus kc. So we will write offset, module of offset is equal to, this minus sign will go 1 upon 1 plus kc. So what conclusion you can make from these two derivation is that the value of offset remains same. The value of offset remains same to both mechanism problem for the proportional controller. Now the next derivation will be a proportional integral controller for servo mechanism control problem. Again a servo mechanism control problem, but it is for now proportional integral controller. So again only GC will change, remaining the whole unity feedback system will remain same. So C of s by R of s is equal to GC upon GC plus tau s plus 1. Is it right? Where this is a proportional integral controller. So transfer function of GC is given by Kc into bracket 1 plus 1 upon tau is. So you have to introduce this GC into the equation. By introducing this equation into the 8.19, C of s by R of s becomes like this. So C of s by R of s, okay, if you see, it is not the first order term, it is becoming a second order, because there is s square, there is s, and there is a constant term. So you will get the equation in terms of s square plus s plus constant. So this is will be a similar to the second order. Is it right? Where we can write this tau into tau 1 upon kc is equal to tau 1, then twice zeta tau, and c by r it can be written as tau 1 s plus 1 upon tau 1 square s square plus twice zeta tau s plus 1. So if the unity step change is introduced into the set point, r infinity or r of t is equal to 1, r of s is equal to 1 by s. Okay, so you have to introduce this 1 by s into the equation. It becomes somewhat longer, okay, but you have to remember these equations because we have studied this during a second order system. So by taking the inverse Laplace of this, it will become c of t is equal to tau 1 upon tau 1 into square root of 1 minus zeta square e raised to zeta t by tau 1 sine of square root of 1 minus zeta square into t by tau 1 plus 1 minus e raised to zeta t by tau 1 upon 1 minus zeta square multiply by sine of square root of 1 minus zeta square t by tau 1 plus tan inverse of 1 minus zeta square bracket square root upon zeta. So you can put again at the steady state value, you can put c infinity. So c infinity becomes equal to 1, r infinity is equal to 1. So what will be the offset? Offset is r infinity minus c infinity, so offset is equal to 0. So if you go to the diagram, graphical representation, you will find for proportional integral there is oscillations but offset is equal to 0. So it is a proof that the offset is 0 for proportional controller for servo mechanism control problem. In a similar way, you can show the offset is again 0 for proportional integral controller for regulator mechanism control problem. So this will be again the last derivation that we will discuss. So here C by U, you can write it from the previous derivation. C by U is equal to 1 upon Gc plus tau s plus 1. But now Gc is here Kc into bracket 1 plus 1 upon tau is. So C of s by U of s can be written like this. Okay, you will solve this equation and you will bring it in form of second year, where now you can write tau 1 square and twice zeta tau 1 because there is no tau. So we can write tau 1 is equal to this and zeta tau twice zeta tau 1 is equal to this. So introduce into the equation C of s by U of s becomes equal to tau s upon tau 1 square s square plus twice zeta tau s plus 1 into Kc. So now C of s you can find out. This will be the equation. So you have to take a inverse of these terms. So you will find this equation is similar to this equation should be tau 1 upon Kc 1 upon tau 1 e raised to zeta t by tau 1 square root of 1 minus zeta square sine of square root of 1 minus zeta square bracket into t by tau 1. So only this equation you will get it, whose again if you put t is equal to infinity, again you will find the c infinity becomes equal to 0, r infinity is equal to 0, offset will be r infinity minus c infinity. So offset is again equal to 0. So what is the conclusion you make? You make that therefore the offset is 0 for both servo and regulator mechanism control problems. So this is how we have discussed the 4 derivations which are frequently asked in examination related to the transient response of the control system, where we derive the 2 derivations for proportional controller for servo mechanism and regulator mechanism problem. Then we discuss about the proportional integral controller for set point change and load variable change, servo and mechanism problem and regulator mechanism problem, and we find out offset is equal to 0. So this is how we can study the characteristics of each and every controller. So remaining part we will discuss in the next lecture. Okay, first of all, go through the book, go through the video lectures, understand the things, and if you doesn't understand, then revert it back to me. Okay, thank you.